And we have 300 horsepower, 440 volts, 60 hertz, 3-phase, 4-pole synchronous motor with an efficiency of 96% and operates at a power factor of 0.9 leading. Okay, so for this one, you'll notice that it says a 4-pole synchronous motor. That don't give you total poles, so that means 4 poles per phase, right? So you only, think about total poles when it very specifically tells you so. And so we'll start now by thinking about the rated torque. And when I ask you for rated torque, it's not torque developed you're going to calculate, but torque output. And the reason for that is P out is the value you have instead of a mechanical power developed by the machine. And so P out is 300 horsepower. And it's 300 horsepower. And we want to convert that to watts before we put numbers in the torque formula. So 746 watts per horsepower. And that gives P out at 223.8 kilowatts. Now, remember that for torque, we also need to know the speed, and these machines run at field speed, and so 120 F divided by P, and we should be getting used to the fact now that the frequency is normally 60. And that means that the numerator in this thing is 7200. And so we got 7200 divided by 4. And that's giving us 1800 RPMs. And so if we put all that into the torque formula, now again, remember that if we don't have PMI, it's torque out that we're calculating. And so that comes from 9.55 times P out and divided by the running speed, which in this case is NS. So 9.55, 223,800 watts, or 223.8 kilowatts. And 1800 RPMs. And torque output now comes out to be 1187. And of course the unit is Newton meters. Okay, now part B. How much reactive power is delivered to the system? How do you know reactive power is delivered to the system? Normally a motor draws reactive power from the system. Here we're told that the power factor is leading. And so that means the motor is overexcited, is acting like a capacitive load instead of an inductive load, which means that it delivers reactive power back to the system. And remember, from the point of view of our power factor correction, then other inductive loads in the system can use that reactive power. Okay, so we want to find Q, and now might be an idea to think about your power triangle. And so if it's leading, it looks like this. Q is going to be capacitive now. This is our ACP in up here, and of course S. And we got to think about where we're going to start and what information can we find. Probably going to find Q last using Pythagoras' theorem. So we got to come up with one of these, what information we've been given. All right, and so I haven't been given any current, so it's efficiency that we got to work from, which means that we have a value for P out, and because we're given an efficiency, that's high. Of course, we'll assume that we're operating at full load. So P out then 223.8 kilowatts. And so from the efficiency formula, and again, we won't bother to put in the times 100% because we'll write our efficiency as a decimal, which of course means 0.96. And so the power in, which we assume of course is AC power in, because we haven't been given anything about a DC rotor source here. And so power in then, power out divided by efficiency. And so remember, power in bigger than power out. And so, just think about that when you're doing this calculation, because you don't want to do it backwards kind of thing. So 223.8 kilowatts divided by 0.96. And so the power at the input, the real power at the input then becomes, I just wrote it out as 233,125 watts, and so I didn't bother to round it yet. So now, that is the real power here. And so, we have the power factor at 0.9 leading. And so we can go ahead now and figure out theta, because we needs it anyway for the power triangle, and we can, pull out a trig function to calculate QC. But what I find is that if you does this the same way every time, then generally you make less mistakes. And so I always goes ahead now and finds S3 phase next. And S3 phase then, again, remember that it's dichotomous, so it's bigger than P in. P in divided by the power factor. And so we have our 233 kilowatts divided by our power factor of 0.9, and the fact that it's leading don't make any difference to the calculation. So S3 phase then is equal to 200, and that should be a 5 there. Uh, 250, and let's round that to 259.3 kVA. So now Q, again, which is leading in this case, so QC from Pythagoras' theorem then, S3 phase squared minus power in squared. And I left out the K's here, and I just said that it's 259.3 squared, subtract 233.1 squared. And I think I put in the 0.125 squared when I did the calculation. Now, if I'm doing it this way, remember I got a K in there in my unit that I left out. So when I actually calculates a value, QC at 113, that's still got the K and it's volt-amps reactive, so kVAR. And so QC, don't forget. And so that is delivered to the system again because we're told that it's leading, which means it's overexcited. Okay, now, how much line current will the motor draw? Normally, if we're going to calculate line current now, we can use either one of the three-phase power equations for P in or S three-phase. And so I line then is equal to S three-phase divided by √3 and V line. If you got a measured value for V line, you should use it, but here we don't. And so the rated value for V line is close enough generally. So 259.3 kVA divided by √3, and we were given the line voltage at 440 volts. And so I line then is equal to 340 amps. And you know, we're working with big numbers there. But remember that what we said about synchronous motors, right? You know, they're really large, 200 horsepower to 20,000 horsepower. And so this one, 300 horsepower, yeah, is a big machine. At 440 volts, we do expect a lot of current there. Okay, so for part D, we're asked to sketch and label a power triangle to represent the machine. We have values for the power triangle now, most of them, except for we didn't calculate theta yet. And so the power factor is 0.9 leading. And of course, that is equal to the cosine of theta, which means that theta is the inverse cosine of the power factor. And so, you know, here, of course, we could also use the inverse tangent of the vertical side of the triangle divided by the horizontal side, which is Q over P in this case. But this calculation is a little bit easier probably. And if you do that, you got 25.84 degrees, and it is leading. So now we were asked to sketch the power triangle. And so instead of me trying to draw it here inside of OneNote, I pulled in a pre-drawn one. And so I'll just go ahead now, copy that over. And so here is the power triangle. Now I put in AC power in as 233 kilowatts. My QC as 113 kVAR. My S3 phase as 259 kVA, and my theta as 25.84 degrees. And remember, the triangle points down because it's a capacitive triangle or a leading triangle.